Hello everyone, my name is Esma Isaidi from New York. Here is my GitHub username, my eDex username, today's date, and my project title, which is Meal Matcher. Meal Matcher is a dietary planning application powered by artificial intelligence and evolutionary computation. The problem I wanted to solve is simple but important. Most nutrition apps treat every user the same. They count calories and that's about it. But what if that person is managing type 2 diabetes, hypertension, high cholesterol, or chronic kidney disease? Genetic calories counting is not just unhelpful, but it could be dangerous. Meal Matcher is different. It calculates personalized nutritional targets, enforces condition-specific medical guardrails, and then generates complete meal plan through one of two engines, each designed to solve different parts of the problem. Authentication is handled with Flask sessions and Vectoid PBKDF2 password hashing with SHA-256 salting. I also built a full password recovery system. It supports both SMTP email verification codes and cryptographically signed URL tokens generated with its dangerous library. Since I've already registered, my credentials are stored in the database. When I submit my email address and password, Flask performs a quick lookup. If my email doesn't exist, the process stops right there. If my email is found, Flask uses a secure hashing function to compare the plain text password I just typed against the encrypted hash stored in the database. If they match, the server grants me access to my account by assigning my user ID to the session. Otherwise, if the password is wrong or if the email doesn't exist, the server stops execution and returns an error message like invalid username or password. So let's log in. Here is the dashboard, and here is the profile page where the clinical math begins. As you can see, we have three panels: physical metrics, medical conditions, dietary preferences, recommended target macros. The values are initially set to defaults, but you can update them with your own information. For example, updating the age, weight, height, activity level, any medical conditions, any preferences. And as you can see here, the program calculates the user basal metabolic rates using the Mifflin-St. Jeor equation, then derives energy expenditures. From that, it set recommended daily calories, protein, carbs, and fat. The calculation runs entirely on the front end in JavaScript. On the dashboard, I can select from the very same 7 supported medical conditions that we saw in the profile. Each one of them activates a specific set of nutritional constraints. For instance, selecting hypertension caps daily sodium at 1,500 milligrams, and chronic kidney disease enforces a hard ceiling of 60 grams of protein per day, regardless of what a high protein goal might otherwise suggest. Let's assume that the user is managing hypertension, high cholesterol, and prefers high protein, low carb, high fiber diet. I have a request that I wrote in advance, so let me paste it and hit generate optimize plan. And here are the results: 4 complete recipes: breakfast, lunch, dinner, and snack. Each one of them with ingredients, step-by-step instructions, estimated prep time, food photography, and link to YouTube tutorials, as you can see here. And here, because I selected hypertension and high cholesterol, the system automatically triggers a deterministic medical risk check, which flags a sodium and cholesterol advisory that compares the meal's sodium and cholesterol content directly against the user daily targets. In this case, as you can see here, for the sodium, the current amount is 670 milligram and the target is 1,500 or less, and for the cholesterol is 200 milligram and the target is 200 milligram or less. What I am most proud architecturally is the dual engine design. The primary engine is the AI wellness assistance. Excels at generating creative human readable recipes, but large language models, LLMs, can sometimes be imprecise with strict numerical constraints, so I built a second engine as a local fallback, a generic portion optimizer. Together, the two engines cover both the creative and the mathematical side of the meal planning. The entire application is built with Flask, SQLite, vanilla JavaScript, and custom CSS, and it's deployed live on pythonanywhere.com, and this was CS50.